Okay, I think we can start. So, hello everybody. My name is Konrad Gądek, and today I will talk about Git. I will show you some fun stuff. I hope you drank your coffee. So at this irresponsible hour, you can hear what I have to talk. During the talk, I hope my quickly scripted thingy will post thingies to Twitter. So, well, you can give me feedback later or something. First question, why bother talking about Git again? Well, for me, the answer is started actually in 2 companies ago and then company ago, and I observed something. This is XKCD, obviously, something that is commonly put onto the slides about Git. I hate it. I really hate it because this is so common. This is exactly my experience, that there is some guy that will help everyone with Git. And nobody actually knows how to do that. Everyone knows few commands like git add, git commit, git push, pull. That's all, and nothing more. This is not something I would like to have, especially since I like to think that Git is more like the ugly duck that never actually became a swan. It's still so powerful, but it's still ugly inside. However, it got nice assistant, or maybe has split personality. Who knows? All right. So to fix the issue with XKCD, first I will start talking about the history, but not the boring part. Only the stuff that actually really matters for understanding why. Then I will show you how Git is actually made. Then I will show you Gore details, but don't worry about that. That really helps. Actually, for me, it really helped and got me from the point of, okay, I know those magic commands, to, okay, now I know what's really happening. Then I will make it fun. I will show you what can we do. This will be seemingly useless, but later I will show you how to make it work for you. And what we learned in the fun section will come handy. So let's start with quickly going through basic terms, just so we know what we're talking about. VCS, version control system. Most of us know that Subversion, Git, Team Foundation, version control, etc., etc. There are many on the market. According to some statistics, Git is the most popular one. The other statistics show that Subversion is still the one, but who knows what's the actual truth. Another thing that we will just briefly need is the hash functions. If you don't know what is that, you only need to know that they take whatever you put. It can be a foobar string or a whole 1 gig file, doesn't matter. They will return the unique result that is very short, usually 40 characters for one of them or so for different. And they are actually very important for multiple things in cryptography today, but for Git they are also handy. Another thing that we will need, this is a bit more involved. This is just the concept that if you go to the restaurant, you want a cup of milk. You don't want to have cup number 67. No, you just want to a cup of milk. And you address things, naming the content. The same stuff. You go to the home and you have the recipe, grab the jar with, I don't know, with, again, milk. You address by the content, not by any other thing. So this is essentially this. Often those two, hash functions and content addressing, come handy, as you can just have 1 gig file or short file with only a string foobar, make a hash of that, and just use that hash to name the thing, and that will work. Also, the last thing, this is the most well-known, this is Linux. Today I will talk about Linux, the kernel, Linux, the operating system is something different. Some people like to name it GNU Linux. Some people like to name it GNU BSD, open something, free software Linux. I will call Linux only the kernel today because of Linus Torvalds, the guy that invented it, actually. So Linux, the kernel of operating system, was created by Linus Torvalds in 1991. And it started like as a hobby project, actually. But then it gained popularity. At that time, the management of the source code was very old. It was using patches, tarballs, boring. Well, that actually worked really well until the point where most people started to recognize the problem that Linus Torvalds, the guy that actually takes full control of the kernel, is starting to become a bottleneck. So he didn't admit that, of course, because he's so awesome. But 3 years later, actually, BitKeeper started hosting Linux. That was a huge improvement and allowed to move forward with that. Unfortunately, not much later, there were some disputes with the BitKeeper owner that led to the discussion of BitKeeper. Basically, the license was revoked. If you want the drama, read Wikipedia and start digging. That's actually pretty interesting and involves the guy that reverse engineered Samba, etc. So, really interesting. So, Linus Torvalds started looking for alternatives, and he looked at many, and he didn't find a proper thing. So he started working on that on 3rd of April. And what I will show you why that it was possible, Git started hosting itself 4 days later. A really magnificent achievement. But I will show you why that was possible. That Git was not like our today's Git. It was involving, required a lot of stuff, but it worked. And it really worked so well that it soon started hosting Linux, starting with 2612. Fast forward, 2017, Microsoft, the old enemy of Linux, as you know, from 90s or early 2000s, is now finishing migration of Windows to Git. This is something that was unbelievable in the 90s. Really, this is astonishing. And they have their own problems. If you go to my Twitter, there are those links. You can dig further. Let's start. So we know why Git was created. Let's start now asking why it's actually needed. So one of the ideas is, okay, actually, why not keep just the latest version of source code? Why not? Well, if that was the case, then I would say that it would be equivalently good to share code with emails. And actually, I done that experiment. I was on university. That was a very simple project. I thought, no, why use Git? Actually, let's share code with email. There were only two of us, and the code was really trivial. And you would be surprised how quickly that came out of hand. Really surprised. I was surprised. And I thought that, yeah, let's keep the experiment going. No, I had to fall back to Git eventually. So no need to thank me. You don't have to do that. There were many problems with that approach, and the most visible one for me was that, okay, I have some email. I have no idea if that contains the feature already that I have, so I have to diff. But still, is that why is that here? And did he remove that, or maybe the guy sent me basing on the version that didn't contain the version? It was really, really, really complex. In so simple application, bookkeeping something for, university course. the problem is, by the way, problem is very common for everyone. If you were ever wondering why infrastructure as a code was created, exactly the same reasons. People like me, like DevOps engineers, just want to have control of what changes. If I go to Jenkins and see, okay, yesterday there was something in this job, the blob, like, I don't know, the combo box, and today it's gone. I have no idea who did that. I have no idea why he did that. Maybe there were other changes. I want to see them in uniformly. But if I don't have good plugins for Jenkins, then I can't do that. And we're talking about only Jenkins. This applies to everything from AWS to, well, everything. So we have this Git, the ugly duck. So the most important thing in understanding how and why actually Git looks like it looks is that Linus created it for himself. This is really important. And initially he had the idea, okay, let's create a low-level thingy that other people would be able to use in creation of other proper version control systems. And he had actually a very good idea of what it should like, and it had to be distributed, which is a good idea, especially if you have an open source community, because where would you put your centralized server? Well, you probably wouldn't be able to, etc., etc. Yeah, and the last part, this is totally Linus, but actually he did that. He did create, in my opinion, the best version control system in the world. Later, the Git became more approachable, etc. But the core of the Git is very Linus Torvaldsy. Let's start with empty scratch, and let's start thinking about one of the use cases. Let's start with one guy that codes something. Let's name him Morty. So he has empty page, and now he wants to do something. I don't know. Let's say he wants a project that lists all of the prime numbers. Of course, Morty is not good at maths, but, well, he tries. So he creates a commit. All right, let's call it M0. And this code contains something. Let's say you can approach this circle. This is rarely explained. Why do I put circle? Why do I put things? So let's explain that. This is a code revision. It contains what Morty wants the code to look like at some point of time. And he created that out of the void. So he created and put it into repo. Awesome. Now he noticed that, okay, I will make some more amendments. Actually, let's commit something. Let's stop here. This is something that is often shown, but nobody explains. Why do you need this small arrow? So, well, this is strictly related to the problem with mailing, to the sharing code with mail. But let's dig into that. So let's say we have this M1. And this M1 contains some code, I don't know, README, one directory, one file inside. And that's awesome. And this file contains error. There is no 2. 2 is a prime number. But Morty didn't knew that. And he made a mistake like everyone does. So now he creates another revision. He learned from mistake and committed, and you can see now that the 2 is there. Let's simplify the diagram a bit. This is exactly the same story. But let's now go to the other universe, where Morty made different mistake. He put 1. 1 is not a prime number. And now in second revision of his code, he fixed that by removing 1. If you look closely, M2 and this second universe, N2, looked exactly the same. They have the same content, but the reason they look the same is completely different. So if you look at those arrows and stuff, every revision, the good intuitions, there are 2. 1, this is a code revision basing on the whole history of previous stuff. I want to the code to look this way, basing on the whole story and my knowledge. The second approach that is equivalently good is, OK, so M2 applies some difference to the history. So M2 says, OK, add 2 to this file. And N2 says, OK, remove 1. This is equivalently good, and if you need intuition, let's continue with that. OK, let's speed up a bit. We saw this thingy. Let's name things. I know I called it revision. In Git, it's called commit. This is a tree, so just a list of files inside that revision. And this is a file that is called a blob in Git. Nothing too exciting. But actually, we just learned a lot about Git. This is so simple. Git has 3 basic types of objects. I will go to that later. But every one of them is content addressed using hash functions. Every one of them is immutable, because if you name something and change something, you create a new object with different name. Because if you have salt, then this is something different than pepper, right? So this is immutable. All objects live in the same place. They live uniformly. They are stored exactly in the same way. So if you ever want to go inside of the .git directory, you'll find them, every one of them. So let's start with this commit, this circle with that says, OK, I'm Morty. I want code to look like that. So it contains the code snapshot. This is the most important thing, but also contains some other metadata. Boring. Let's speed up a bit. What actually commit looks like? Let's dig into that. So we're Morty, and we look at the newest version, so don't mind the comments too much. And we can see, in the first line, you can see a tree. So this says, all right, this commit has this version of files. And you don't see actual files here. You have a hash, because Git names this way. This lengthy 40 digits, actually not digits, but hex numbers. This is it. This states where is the description of what I want the code to look like. And other things like parent, we discussed. Parent, commit, the arrows. So this says, OK, this is a backwards arrow. These are the commits that I had looked at, and this is one of the successors. Sorry. And we have other things like author, committer, don't worry about that, and commit message. We have this. So let's make it more interesting. I hope you drank your coffee. So we have now Rick. Rick is his grandpa, and he is crazy scientist, but he knows stuff. So he noticed that M1 contained an error. It didn't have 2, because Morty missed the number 2 from the list of prime numbers. And he codes that. But he doesn't share his code, because he's lazy. So Morty doesn't know about that and just creates his version of file with the number 2 added. If we know everything, then we can see the problem that is incoming. And Morty will learn about that very quickly, because soon Grandpa will share, yeah, Morty, so I did that fix. So now Morty knows about this version. However, Grandpa doesn't listen. He only cares about himself. So he codes another thing and adds another, 20 or 50 more prime numbers. And Morty is not aware of this last thingy. And neither Morty nor Rick knows that there's this sister Summer that coded something else. She added Fibonacci numbers, or whatever she calls that, in 2 versions. That is becoming complex, and I will say that this thing is already nearly impossible to manage using mail. So that's why version control systems exist. So how do they help? And this will come, how do they help actually? So we had this situation, and we want to be able to do this. We all know that, probably, most of us. We want to merge histories. What does it mean? Actually, it's a very simple concept. You take things that one guy introduced and the other guy introduced and make something that contains both features. In this case, fixing a bug twice, probably the same, but maybe not. So, interesting thing about Git is because Git is local. Everything you have, when you clone the repo, you have a whole history, is that you can, the Git can easily trace M1. M1 is the common commit for M3 and R2. If you saw that, you know that M2 and R2 need to be merged, and M1 is the common thingy. This is very important because it's giving the algorithms way more information, and they make differentials. They make merges way more pleasant, really. This is important. We got this situation, and basically nothing changes. We can merge anything we like. What is a tree? Back to our discussion. So we have a commit, we have a tree, and you can see again our commit in the first thingy. But then we saw this tree and description. So let's look at what's inside, and you can see that it's very simple. It is just a list of descriptions and files, and not files by their content, but again by the name that they the hash of the place where they are actually stored. So you can see a README that is named by the hash, and this is a file. But also you can see the directory called primes, and it's called a tree, so you have a reference to another tree. And yeah, everything is so uniform. What is a blob? So I talked about the file, let's look inside, and it's that simple. You just require the file that is named like README or files, and you just get the result. Everything in Git is actually stored similarly. It's stored like a file system, and this is the basis of Git. And that's why Linus was able to host Git itself inside of Git after 4 days. It was mundane, but it was possible. If you ever go to .git directory, you might be surprised. Wait, I told you that they should be readable. There are files named by the hash, right? Well, actually, I did not lie. You have to unzip it. And that's all. You have just the description. So this object is a blob. It contains, I don't know if that's visible, but first 2 digits are just the length of the content. And then you have the content. Nothing changes. And this information alone can help you in very dire situations. There was a case on the internet when a guy had a broken repo. And Git said, sorry, assertion error. The file doesn't match with the hash function. Why did that happen? Random bit flip. That really happens from time to time. And he didn't have a backup. And he started digging, and because of that architecture, he was able to trace that one file that was changed, and he then brute forced, because he was flipping one, he assumed that there's one bit flip, so he flipped every single one of them until the hash was right. And interesting thing is that if we didn't have hashes, that error would go unnoticed. And you would be really surprised how often bit flips, random bit flips happen. You can Google I think that was CERN or NASA that shared the investigation, but that's quite a bit of bit flips per gig per year. As I said, Git inside is a very ugly duck. It stores everything, naming that by the hash, a long hash. Nobody remembers that. So you may know the things like master or feature branch. What are they? Actually, they live there in .git/refs. And they are, again, very simple. They are just files that contain hash. Nothing else. If you have remotes, this works exactly the same. This is so simple, and yet so powerful. And we need one more thing just to go into fun part. What is stage? This confuses a lot of people, especially those coming from Subversion or others. What is stage? What is git add? Why do you need that? So the staging area, sometimes called index, is a thingy that you create on the go. It's actually a tree. If you're working on your files in your file system, which is called a working directory, you just make changes. And now Git compares that to temporary tree that it will use to store files. And this temporary tree is called staging area. If you have this prepared tree that you prepare by adding stuff, git add, git rm stuff, don't remember that now. But if you do that, you create just this tree. And if you then just create a commit, it will take, OK, I have this tree, let's take it. Nothing else. Why do we need that, actually? Because, well, we probably would go away a long way without having this separate stage, without having index. But it's very, very, very handy. I'm a lazy programmer. I have to admit that. And I code in a chaotic way as well. I just code a lot of stuff immediately. If I code a lot of things, that would make my commits unreadable. However, because of the Git's way, I am able to recover. Because I code for, I don't know, 2 hours, 3 hours, something like that. And then I want, yes, I'm happy with the result. So then I can add the files and just go along. But I can also use another commands. Actually, I recommend always to use GUI because it's way, way faster. But you can take some part of the actual file you have on the disk and say, Git, take this part of the file, only those lines that I changed, not the others, only those ones. Apply that to the staging area, and then I can commit. I can make 10 commits out of my changes, and that makes a lot of difference in my commit history. It makes it really readable. You have also Git Stash. Git Stash is another cool tool. It takes every change you have in your working directory. How does it know the difference? It compares to the tree from the last commit. So it takes all the changes in your directory, creates a tree, creates a fake commit inside. You don't have to know that. And now you have a clean directory. You can continue. Inside, this is still the same things, like blobs, trees, commits. Really, Git Stash is creating a commit inside. That was interesting to me to learn as well. Now we know all that is required to have fun. So let's continue. We have this. And we probably know that we can do merge. And merge by creating this commit number M3, which is nice. But we can do better. Let's say Summer, she doesn't know about any of M1, R2, any of that. She just has her S2. But then she learns about that and says, nah, I don't like those things. However, M1 is looking good. I want that commit. So she takes that. Because why not? Because Git inside is just those simple things. Files, trees, commits. Git can very well take just the M1, say, OK, this is the difference from M0, because it knows everything, because why not? And then apply that to S2, because why not? This is everything. Everything is actually possible having this approach, because we have full power. That's why I call it ugly duck. More, Rebase. Let's say the Summer, actually wants R2 and R3 because she likes those, but doesn't like M1. Neither she likes M2 because she doesn't like her brother, Morty. But Grandpa makes a difference, so he made good commits. So she can cherry pick. I can use Rebase, which is actually a cherry pick on steroids. And she can just take those two files, because why not? Nobody prevents us from doing that. And if we wanted to, we could go to Git internals and code that our way. Submodules. I wanted to talk about that because they are so common, and sometimes people use them to help with other stuff. And you have this big repository, and now you say, OK, there is a separate repository, like, I don't know, Linux kernel, and I want to embed that into my web application, because why not? 2017, everything is in JavaScript, right? And the usual answer to my answer to submodules is never ever touch them. This is a good rule of thumb. I was in so many teams that use submodules, and in every one of them that was a pain. You would be surprised. And the reason for that is because they require everyone from the team, really everyone, to never ever make a mistake if they use submodules. There are better ways I will show you later. Actually, yeah, so we have this submodule problem, and we want to do better. So let's say we want to merge this Git history of Linux, the kernel of the operating system. And how can we do that without submodules? And the answer is subtree, actually. We have those files, like, okay, we have README, we have some primes that are probably not correct, but we want a Linux kernel inside one of the directories. So what prevents us? And this is a really question to you. Why we can't do that? And the answer is, yes, we can. Because Git stores things like key value. We just throw everything the Linux kernel has inside, so we have all those orange commits inside. And now we can create another tree that says, okay, a commit, sorry, M5, that says, okay, my tree contains README that I have already, the primes number, which is a separate tree that I had, and Linux, which is a separate tree, because Git doesn't care what is the source of that tree, where did that come from. It only knows, yeah, I have this tree, yeah, so no problem. And this is a subtree strategy. There's a tool called git subtree. If you ever want to get submodules, use subtree instead. This is really, my team doesn't even know that I'm using subtree, and it helps us, the DevOps, greatly. So no problem. Not mentioned here because I have very little time. I have no idea because the screensaver went. But the git rarera, this is a very obscure thing. If you play with merging stuff and you resolve the same merge conflicts once and again, then enable git rarera, which is basically, I don't recall exact translation of rarera because it's so obscure, but it just stores the resolution of the your merge conflict, and if it sees the same conflict again, it will apply that. Really awesome stuff, and enable that and play with that. Reflog, because everything in Git is an object, and you create a lot of objects. If you happen to remove your branch, then it's probably still there, because Git uses garbage collector, by the way, and the branch is probably still there, so using git reflog you can recover because it has history of where you were. Awesome stuff, can save you if you know that. Just keep in mind that if you screw up, you can recover. That's a good tip. And then go to Stack Overflow, they show how to do that actually. Git filter branch. If you want to do some weird stuff with your branches, this is probably the command to go, because you can say, on every branch, go through whole history, rewrite that, removing that file. You will create a separate history, by the way, but this can actually work for you. This is a very powerful command, and never ever use that, or your team won't be too happy. Git tag, something that many people know. The interesting thing is that git tag behaves exactly the same way like references. So you just name thing, but that thing is immutable. And another interesting thing is that git tag can point to any object, not only a commit, not only a tree. It can point to a blob. And interesting thing is that I think it was in the Git repository itself. There was a tag that pointed to a file containing the GPG key of the maintainer. Useful case, probably for some. And yeah, you can sign every commit you have. If you need super security, maybe you can use that. Garbage collection. This is really something that is worth mentioning just for the sake of having you to know that files and objects are created on the go, sometimes they create some stale files. They will be eventually removed, and that's all. You don't have to worry about the disk space. Okay, fun stuff done. Let's make it work for us. Something that I encountered already was that there were at least 3 big discussions in my life where people were discussing over hours and hours what is the best Git flow for them. And they were fighting. And I will say that this is not that important as you may think, because Git is flexible. If you make a mistake, just transition to another. But also, there's no perfect workflow. And every of them has good and bad parts. Like this linear history, it's super easy to follow, and many people from continuous deployment area say this is the best thing for them. And probably it is, but remember about the trade-offs. Instead of branches, you have to use feature toggles. And how do you perform code review? Probably you don't do pre-commit code review, but post-commit, so you just review later what you changed. And yeah, and requires a lot of tests, because usually you have that and you have continuous deployment, so you want your thingy really tested very often. But I'm not a big fan of that, but for some projects it makes perfect sense. Actually, I use that for some of mine, because they don't require feature branches, because I just need velocity. Like if I break something, I can fix that, and that's quicker than reviewing myself. Pull request, aka feature branches. This is the most used thingy, and not without a reason. It's simple. It delivers. I would, if you don't know what to use this one. It has some problems. For example, if you have the merge pane is a function, as we learned yesterday, of the time that we recently merged. So if it is a great time, then a great pane, and also the size of that. If we have this feature branch that is long running, then we can have pane. But oh well. So let's make that a bit easier. Let's say we work. We can recover. We can merge back from master to our thingy, and if we can do that often, the pain will be lower. However, please note that this merge thingies are just a bloat. They are really a bloat, and here we have many of them, at least 3. So this introduces a bloat, and this is a trade-off. Rebase. Rebase is something similar to feature branches, but instead of merging, you just use and you can update as well, just because some people believe it's not true, but no. You can update rebase often, and there will be little pain merging, and you can just do that. Why not? This is exactly like merging in feature branches, but you just make history linear. Sometimes that makes sense. Rebasing could potentially make some more merge conflicts. Never met that situation in my life, but it could. And also you can have pull requests, because you review the thingy while it is on the feature branch, and if it's okay, you just rebase and you recover to the linear history. However, it requires the team to understand what is rebase. The cool stuff about rebase, you can squash, because Git uses only commits, trees. Why not squash? Why not? It has just one downside, or actually a benefit. You lose history of that branch. If you have your feature branch with ton of useless commits, probably this is a good idea. If you have a feature branch with lots of important commits that have very different semantics, probably I would say that don't squash. But the trade-off at your project is something that is your decision. And I wanted just to show one more thing, and this scares a lot of people. This is git flow, and looks so complicated. But if you look closely, you can see that actually this is a feature branches on steroids. And if you need to have support for long-running version 1, then probably you want to have separate branch for that. Why not? If you want to have hot fixes that are done really quickly for the client while you don't disturb the team preparing the next release, also you may want to have separate hot fixes. This is all about the git flow is very easy as soon as you realize that that everything has the reason for existence. Like feature branches exist there, so at any time in the history you can just merge to develop and prepare the next version. Or if you want to take that develop and not to merge that feature that is halfly done, you just don't have to do that now. You can wait till the sprint ends, merge, develop, create release for the client, and do other stuff. And this is not the full form, by the way, because you can do much more fun stuff like, okay, if you have to support 15 last versions of your application, create a one branch for each of them. And apply hotfixes, apply, cherry pick all the security stuff that you have to apply for all versions. You can do that, because why not? So I hope that I showed you, well, I showed you just a bit of that, but I hope that it will help you actually understand Git. For me, understanding it, a bit of internals really helped knowing what's happening. And that really helps knowing what's happening with those weird workflows like git-flow, which looks very hard, but it's not. Okay, do you have any questions? Good questions, bad questions, doesn't matter. Everything is actually a good question. Okay, in that way, thank you very much.